Hi, my name is Tim Metcalfe from Duo-Gard Industries, and today we're talking about daylight modeling. Daylight modeling is a service that allows the architect to look at the virtual environment and look at his space to make meaningful and important changes to his design and the structure of his building. We take into account things as its global position and its weather data for the specific location. A little background information on daylight. Daylight is visible spectrum between 380 and 780 nanometers. It is the light reflected back to the eye, which is a visible range in green, blue, and red. We're talking about the solar spectrum light, not irradiance or UV light, but the light that can be registered by the human eye. When we're talking about the photometric properties of light, we're talking about luminous flux, which is the source of light, and the intensity, the luminous intensity of the light, is how it travels through the air. And when it hits a surface, we're talking about a luminance. And then when it's reflected back to the eye, then we're talking about luminance. So a candle weight or candle power equals 1 candela as far as units go. How does that translate into lumens? A candle is about 4 lumens. A regular 100-watt light bulb is about 1,600 lumens, and then a 13-watt fluorescent bulb is the same 1,600 lumens. There's some of the luminance values as expressed by Harvard Design School. Sunny day is between 70,000 and 100,000 lux outside, and a few other readings like moonlight is 1 lux or 1/10 of a foot candle, but we can still see by it. So there's just some different values here from AIA Lighting Handbook that expresses typical values outside. So metrics, units of measure that we talk about in daylight, we have candelas, which is what comes from the source. In our case, in daylight modeling, it's the sun. That's our source. And as lumens is the flow of light from the space, which means like if you had a shower and you turn the shower head on, the water falling into the bottom of the tub would be the lumens, or the flow of light from the source. We've got lux, which is measured in lumens per meter squared, and foot candles, which is measured in lumens per foot squared. Same unit, just a different form of measurement. So we have a luminance, which is the amount of light that hits the surface again, and luminance, that is the amount of light reflected from the source. Geographic integration is a large part of what Duo-Gard's theory on daylight is, meaning that not every application takes the same materials. We want to use different materials in a cold climate than we do in a hot climate. It depends on what's important. Is solar heat gain a good thing in a cold environment in winter? Absolutely. Is it a bad thing in a hot, humid environment? Absolutely. It makes your air conditioning run that much longer. So geographic integration is a big part of what we're looking at when we're looking at your daylight model. Now, in this simple gymnasium going forward, we're taking a tour around the outside. We're showing it as a 2-foot clear story around on all 4 sides, and that it's a simple gymnasium with the same clear story. We chose 2 feet because one of the Duo-Gard advantages of polycarbonate is that you don't need as much as you would with, say, a different translucent material. We're showing in a false color grid the amount of light that goes around the space. As you can see, the more yellow areas are south and west in this application because the weather file is from Detroit. So radiance. So the same space, the simple gymnasium space, is September 21st at noon. And what's important about this is where the light travels and the values. So for school, that 30-foot candles is the basic goal for daylighting. We have an ample amount of light on the equinox, and the equinox is important because it's equal day and equal night. So what is Radiance anyway? Radiance is a backwards ray tracer. It was created by Greg Ward at Lawrence Berkeley National Labs. It's a series of Unix programs linked together, and it gives you a lighting level at a specific time, a point in time, meaning like September 21st at noon or October 12th at 3:30 in the afternoon. Either way, you can get an illuminance value at a given point in time. It's validated software, and it's a gold standard for analysis in this way. So daylight autonomy is another way we look at daylight. Daylight autonomy is goal-based, which means for a certain lighting level, say 50-foot candles in this case, between the hours of 8 a.m. and 5 p.m., you can expect to reach the goal what percent of the time. In this case, it's about 75%. And you can see that from the grid below. So daylight autonomy uses radiance to calculate its values. They have 15-minute runs based throughout the year. It's goal-based, and it's developed by Christoph Reinhardt while at the NRC, and it uses weather-weighted data from U.S. Department of Energy or another source. So along with basic radiance and daylight autonomy, other ways or other analysis methods that we use to look at the space are volumetrics. Now, volumetrics is a way to fill this entire space with grid sensors. If we look at the same simple gymnasium, now if we cut through the space horizontally in three different, every 6 inches or so, we can see the light gets more intense as we go up to the source, and then it spreads out more as we get further away. The intensity changes, but the light spreads over the space, and that's important to where you're going to be playing your sports activities in your line of sight. If you have younger kids, you're going to be playing at 3 feet. If you have an average size high school kid, you're at 5 foot. And those values are going to be different for line of sight to the basket. We also do 3D grid analysis. What this means is we're showing in a 3D grid how the light travels as it gets closer to the source. And as you see, as it gets higher and higher up to the source, the intensity on the one side gets higher and higher and higher, and that's represented in a 3D grid. The 3D grid goes back down, and we've got a source that starts to level out, and the orange on the back side, the north side in this case, starts to brighten up, meaning at eye level, it's very much evenly distributed. When we do daylight models, we look at glare. Glare can be a problem for life safety issues in pools. It can be in your regular office space as far as solar heat gain. Glare is measured in luminance, or candelas per meter squared. And as a reading of 2,500 candelas per meter squared or higher could be considered glare and cause discomfort to people within the space. In addition to the luminance or candelas per meter squared, the contrast ratio is important. You have a contrast ratio of 10 to 1 or greater, you have a light adjustment the human eye cannot react to this spread in light, meaning the lights become really light and the darks become really dark, and your eye can't adjust between the two, and it makes it for an uncomfortable space to be in. So when we're running your daylight analysis, we want to make sure that the contrast ratio is good, and also you don't have a glary space to be in. An illustration of a glary space here is the south side windows, and you can see as the sun on December 21st runs through the projected time for Detroit, you can see on the display that the light travels throughout the space all day long, but it never leaves it. And there's glare somewhere inside the space all day long. So that's an issue for solar heat gain, it's an issue for contrast, it's an issue for comfortable space to be in and occupant behavior. Partners in daylight with Duo-Gard, ABIPS of Boston, MIT, Harvard Medical School, University of Michigan, Harvard Graduate School of Design, just to name a few. We're always looking for new and exciting opportunities with many of these schools and personalities.